Part B. Problem B1. This problem consists of four questions. We need to analyze oscillation for next setup like this. A certain mechanical oscillation can be modeled as an ideal massless spring connected to movable plate on incline. The spring has a spring constant K. The plate has mass M, and the incline makes an angle theta with the horizontal. When the system is operating correctly, the plate oscillates between points A and B. This point and this point. In a figure located at distance apart L. When the plate reached point A, it has a zero kinetic energy, but then trips a small lever that instantaneously loads a block of mass big M on the plate. The block and the plate then move down the incline to point B. This is point B, and this is point A. Part B. Problem B1. It has four consequent questions to analyze some kind of oscillation, where we have a setup for this on the picture. A certain mechanical oscillator can be modeled as an ideal massless spring connected to a movable plate on an incline. The spring has a spring constant K, the plate has mass M, and the incline makes an angle theta with the horizontal. When the system is operating correctly, the plate oscillates between point A and B without friction. They are located on distance L between each other. When the plate reaches point A, it has a kinetic energy 0, but then trips a small lever that instantaneously loads a block of mass big M on the plate. The block and the plate then move down the incline to point B, where the force from the spring stops the plate. At this point, the block falls through a hole in an incline, allowing the plate to move back up under the force of the spring. Upon returning to point A, it collects another block, and the cycle repeats. Both the plate and the block have a coefficient of friction mu. Here we have coefficient of friction mu. With the incline for both kinetic and static friction. It is reasonable that motion in either direction is a simple harmonic in nature. So, question A. Let's mu c be a critical value of the coefficient of friction where the block will just start to slide under the force of the gravity on incline. Then let mu equal mu critical over 2. So find the mu in terms of M, big M, G, and theta. And this is the first question. So here we know that to write equation for motion on incline, we have MA equal mg sine theta minus mu mg cosine theta. So for critical angle we have this part exactly equal to 0. So it means that mu critical equal tangent theta. So this is what we need, because mu equal mu critical over tangent theta, and to express this one through these parameters, we can just simply write that it's tangent theta over 2. So this is the answer. Mu equal tangent theta over 2. Question B. In order for a system to move correctly, it is necessary to have the correct ratio between two masses, big M and the small m. These masses are chosen so that the downward moving block and the plate just stop at point B, while the upward moving plate just stop at point A. Find the ratio big M over small m. So here we need to use energy approach. So it means that initially both blocks not moving, so kinetic energy is 0, and afterwards, after one cycle, again both blocks stop and kinetic energy is 0. It means that we have to equalize energies getting from gravity and spent through friction. So total energy taken from gravity is energy for this block to go down, which is mg multiplied by L and sine theta. And this energy we will spend for friction, for work of force of friction made by this block moving upward and these two blocks moving downward. And we can count this work, which is this block up, that will be mu mg L cosine theta, and down we have mu m plus m g L cosine theta. And of course this energy must be equal to this energy, so we can rewrite this equation here. And count everything. So we have this relation. So after we, because we have mu equal tangent theta over 2, we can put it here. Oh, this is not correct. This is sine theta. So we can move this cosine to the left, so that will be tangent theta. Instead of mu, we can put tangent theta over 2, and finally we have such expression m equal 1/2 m plus m plus m over 2. And from here we have, what do we have? We have m over 2 equal m. So this is our relation. We have m over m equal 2. This is the answer. Question C. The system delivers block to point B with a period t0 from A to B until the block runs out. After that, the plane along oscillates with period t prime. So after that, this plane could oscillate with the period t prime. We need to find the ratio t0 over t prime, like this. So here we just need to mention that motion on this plane with the friction, it's a simple harmonic motion, and friction just changed the point of equilibrium, but it's not affected the period itself. So it means that the full period for mass m will be 2 pi root m over k. So it means that to find what is t0, that will be motion here, that's half of period for this block and the half of period for this two blocks. So that will be pi root m over k plus pi root m plus m, which is 3m over k. And the period for this plane as a separate is this one. So it means that t0 over t prime, that's equal, this is t prime, that's equal to 1 plus root 3 over 2. So that's the answer for this question. This is a relation for these two periods. This is 3. Okay. Question D. The plate only oscillates a few times after delivering the last block. At what distance up the incline, measured from point B, does the plate come to a permanent stop? So, as I mentioned in the part C, we see that motion from point B to point A, it's a simple harmonic motion. It means that for this way we have point of equilibrium is right in the middle, L over 2 from point B. But what happens if we are moving down? If we are moving down, the direction for force of friction change, and because it's equal to mu mg cosine theta, so it means that we need to change this force twice and make equilibrium in point ky equal 2 times mu mg cosine theta, where y is how further this equilibrium shift from midpoint right here. And because mu equal tangent over 2, so that will be equal exactly mg sine theta. So this is how to find this shift for second equilibrium for motion down. That will be mg sine theta over k. Okay, now let's see what happened. We have oscillations up and down, and obviously this oscillation will stop when next stop point will be between this equilibrium and this equilibrium. It means that if we are going down and finally we stop further than this point, it will permanently stop. And same thing for other way. If we are going up and stop below this point, after that we will not move down, because this will be our equilibrium point. So this is the solution. Let's write it down. When we first going down, we will stop in a distance L minus 2 mg sine theta over k from point of B, somewhere in here. And after that, when we will go down, we will stop in point two times 2 mg sine theta over k, and so on. So each time we will move, we have, after n oscillations, we have, for the motion up, we have distance from point B is n times 2 mg sine theta over k, and when we are going down, stop point is L minus n times 2 mg sine theta over k. So we just need to count if this distance is greater than L over 2, or this distance less than this equilibrium point. So we can write these conditions down. So first condition is n 2n mg sine theta over k must be greater than L over 2, and the second condition is L minus n 2 times n mg sine theta over k, that must be less than L over 2 plus mg sine theta over k. Or we can rewrite this expression in form of n plus 1 over 2 times mg sine theta over k, that must be greater than L over 2. So this is the solution. Either this one, if it comes first, or this one, if it comes first.